Sleeping through disasters. We have all been there. You're on call and you get paged at 3 a.m. and you have to try to remediate the problem as quickly as possible. But what if you could put together an architecture that could handle recovery for you? We will demonstrate how to do this during this presentation. To start things off, I am Ryan Cook. I will be going through and describing the components that will be used to accomplish our solution of making on-call easier, allowing you to sleep through disasters. For a second half of the presentation, Mario Vasquez is going to perform a demo of all of these pieces working together. So, the problem statement. With the adoption of OpenShift and Kubernetes, application resiliency has become easier and more approachable than ever before. But what do you do when that's not enough? With the combination of multiple OpenShift clusters, data replication, and application placement and management tooling, an architecture can be implemented that would allow for a failure of a node, cluster, or even a data center. At this point, you're thinking, everyone already knows this, and that is hard. How do we actually get there? In this presentation, we're going to show you how. So, as you can see with this diagram, there's a lot going on. We're going to introduce a lot of cool tooling and a lot of cool projects and how they can be paired together. Starting here, we see how we can make an application resilient through the usage of two clusters, one in Europe and one in the United States. We have a load balancer that sits in front of our application, and our persistent application data is replicated from Europe to the cluster in the United States. So, when a disaster occurs, the cluster in Europe goes offline. Our company is still operational because our data is replicated. Our application is operational thanks to tooling and our load balancer's management of traffic. So here are the items we're going to cover, allowing for on-call to become effortless. Integrating these pieces together will create a more resilient environment for your applications to run, lowering the possibility of major downtime. We're going to approach this by providing best practices, starting at the application first, and then discussing tooling that can be implemented that will allow for multi-cluster to be approachable. We can add all the tooling that we want, but without setting best practices in how we manage, deploy, and define applications, we won't be able to mitigate potential outages, regardless if it's a single data center or multiple. GitOps. I'm sure at this point you've heard all about GitOps. When I talk about GitOps in this presentation, I'm talking about all of your YAML living in Git. Before we can even begin to get started ensuring that we can mitigate outages, we must start here. Why? Having all of your YAML within Git allows for you to manage the state of your application regardless of the cluster that it's deployed upon. You can even go as extreme as having Git manage your GitOps and management tooling. Mario will actually be showing this later on in the presentation. A major win for investing in GitOps is that in the case of an extreme emergency, the items within the Git repository can be used to recreate your applications without worrying about missing components or missing objects. This also allows for you to have a mature promotion cycle of your code. The items that you are developing can easily be sent as a PR to be pushed to your pre-production and production environments. One decision you will have to make is whether to use branches or customize. The one important thing to note is that most GitOps tooling supports both methods for storing your configuration. In my opinion, probes are incredibly important. There are two kinds of probes, liveness and readiness. At a high level, liveness probes ensure that the application is still running and has not thrown an error that stops your application but does not force a pod to restart. Readiness is a check that identified that a pod is ready for traffic or utilization. Links have been provided to the Kubernetes documentation showing some samples and best practices. Defining these checks correctly and in a way that reflects how your application operates will allow for self-healing to occur. Tooling is how we are going to go from doing well, manage our application on one cluster, to managing our application amongst many clusters. This presentation will focus on Red Hat Advanced Cluster Management, or RHACM, for our GitOps tooling. If you've never heard of RHACM, then you're in luck. Mario is going to be giving an excellent breakdown showing the functionality. RHACM provides the ability to manage application placement on a single or multiple clusters based on labeling. In the event of an absolute disaster, or if your organization operates with the concept that OpenShift clusters are cows rather than pets, RHACM can add or remove clusters. Labeling also allows for these clusters to receive the application without manual intervention. RHACM can also integrate with existing Argo CD deployments, and in future releases will offer tighter integration between the two products. Policies can be added to clusters to mitigate and identify security risks. One other functionality that I'd like to identify within RHACM is that there is the ability to update your OpenShift clusters from within RHACM. During this demonstration, we will be defining our application and placement from a configuration that is stored within a Git repository, proving that we are all in on GitOps. In the unlikely event that we would need to recreate RHACM, then we can immediately apply these YAML files to our cluster where RHACM runs, and our application will be visible and managed by RHACM again. So, load balancing. Load balancing is a must when working with multiple clusters. This could be a global load balancing solution such as Cloudflare, an internal load balancing appliance such as F5, or even an HA proxy instance. The important factor when using a load balancer is to ensure that the traffic routing is based off of a health check that accurately reflects your application. Similar to readiness checks we talked about earlier, we want to route or reroute traffic with a strict failure threshold once it's met. To ensure that persistent data is replicated between our clusters, the open source project Scribe is used. Scribe allows for various replication methods to work, whether it's one-to-one or one-to-many. This demonstration, we will focus on using rsync, but check out the project on GitHub to learn about the other methods. Scribe allows for us to define how frequently we would like to replicate the persistent data to our failover site. The schedule of this replication is based on cron. So, for example, you can replicate the data once a day or as aggressive as every minute. Depending on the application, certain copy methods can be used by Scribe. The demonstration will show the none method. The none method mounts the PVC, copies all the data to the destination. This would not be a good method to use for applications such as databases. The methods clone and snapshot will take a copy of the PVC first, create a PVC based on that snapshot or clone, and replicate the data to the destination, allowing for the data to either be placed at the failover site as a snapshot or written immediately to the PVC. So, for example, with a database, you might want to use snapshot to snapshot at both source and destination. The copy method, though, is defined, like I said, at both source and destination, so they could be mixed, where one cluster may use the none method while the other one uses a snapshot. The last piece, although optional, allows for secure communication between the clusters. We are specifically using this for our data replication with Scribe. But why? Although Scribe has the ability to use load balancers or node ports for cross-cluster replication, we want to be able to identify and store a replication service endpoint in YAML within Git. This allows for us to know exactly the name rather than needing to go to the cluster and identify the load balancer that may have been created. As you'll see on the slide here, we talk about GlobalNet. What is GlobalNet? GlobalNet allows for network ranges to overlap. So, for example, if you've installed OpenShift with all of the default values, then your service and pod networks are the same. And if you have multiple clusters, that means they're the same on many clusters. With the help of GlobalNet, cross-cluster communication can be conducted without needing to make major changes or to redeploy your OpenShift cluster. With the use of Submariner and the secure cross-cluster communication, if an OpenShift cluster is low on resources, you can migrate a portion of this application to another cluster, while maintaining the same service routes even though the application may be running on two different clusters. At this point, I will pass off to Mario to demonstrate and show all of these pieces working together flawlessly.
Thank you, Ryan. So before deploying our application, let's see the clusters that we have available to use. So if we go to clusters, we can see that we have three clusters. The local cluster is the cluster where RHACM is running, and we have two managed clusters, EU cluster and US cluster. We are going to deploy our application to both EU and US clusters. EU will be our primary site, and we will use US site as backup site. So with that being said, we can go to applications and get started. So as you can see, we don't have any applications yet. We have everything in our Git repo, as Ryan mentioned. So all the files in order to deploy our application, in order to deploy Scribe and all that stuff, we have them on Git. And also we have different applications that will be created by ACM. And those applications are defined on Git as well. So the only thing that we need to do here is add that repo that has all our applications, and ACM will do the heavy lifting for us. So we click on create application. We are going to give it a fancy name. We are going to choose a namespace. In this case, it will be RHACM apps. And then we are going to choose the repository type. In this case, we are using a Git repo. So we choose that. The repo that we will be using is this one, which is on GitHub. We need to choose the branch where our applications are. In this case, those applications are on RHACM apps branch. We are not using any folder, so all our files are in the root folder for this branch. And then as reconcile option, we have merge or replace. In this case, we will be using merge, which means that if the object that we are trying to create already exists, we only merge the differences. Replace will remove the old object, well, will replace the old object by the one stored in Git. We can also create pre and post deployment tasks. This is very interesting. For example, if you're working with network equipment and you need to configure it before deploying your application or after deploying your application, you can define more complex workflows like, okay, before deploying my application, I will open a ticket on our ticketing system mentioning that a network configuration is changing, and then I will deploy the application, and as a post deployment, I will configure the network equipment and close the ticket, for example. That can be done, and it uses Ansible under the hood. Next, we need to choose where we are going to deploy this application. In this case, we are going to deploy it on the local cluster, so on the cluster running RHACM. Why? Because what we are deploying here are the definitions for all our applications that we have on Git. So in this case, RHACM will load that information and will create the different applications for us. Last but not least, we can choose the application behavior, and in this case, the deployment window. This is really interesting when you have only specific intervals of time where you can make or you cannot make changes. So you can basically say, okay, this application will be active from Monday to Wednesday, and then you can choose the time zone and the start and end time, or the whole day if you don't set anything here. So this is really interesting for more complex scenarios, right? In this case, we are going to set it to always active since we want it to work right away. And one last thing that I want to show you is that all that stuff that we did on the web UI can be done using YAML, because at the end of the day, this is all Kubernetes objects, right? So if we click here, we can see how we get the YAML that will be sent to our OpenShift cluster, right? We have a subscription and we have a placement rule. These three objects are part of the RHACM APIs. So at this point, we can click save. Okay, we will get redirected to the application and we will see our application topology. So as you can see, we have an application. That application has a subscription. The subscription is attached to a placement rule, and then that's attached itself to a cluster. So we are deploying this application into this cluster, in this case local cluster, and this subscription has created um, different objects. For example, we can see that it created a placement rule called cluster EU cluster, another one which is called cluster US, with that will match our US cluster, then another placement rule that will match both clusters, EU and US. Then we have the Scribe application, the Scribe subscription, the Scribe configuration application, and as well the subscription. So let's review. All right, so we can see that we have all our application here. So let's review the Scribe application, for example. So here we have a pretty clear view of what is being deployed to our clusters. Now the same happens for the different applications that we deployed. For example, the uploader application, it's deployed to both clusters as well, and it has a route, a service, namespace, deployment, a persistent volume claim. So it seems that everything is running. So let's go ahead and let's try our application. Right, so our application is running. So let's try to upload some files here. So let's see the list of uploaded files. As you can see, it's empty. So let's upload some. Okay, so let's try to upload some of these files. Okay, we got one. Let's upload this one as well. Okay, and now we can see that we have both files uploaded. Okay, so everything it's running properly, but now we need to create some chaos. So let's go to the EC2 console. These are the instances for our EU cluster. So why we don't go ahead and stop them? Okay, so now we are going to go back to RHACM and see how the cluster moves from ready to not ready. All right, so we can see how our EU cluster went offline. So let's see what happened to our applications. So now if we go to, for example, the uploader application, we can see that it's only running on the US cluster since we lost the EU cluster. So same will happen for our Scribe application and actually for any application that was running on the EU cluster. But if we go to the uploader application and we refresh the page, we'll see that the application is still running because we have our US site now acting as primary site, and that we can see the uploaded files here. Okay, so and now we can even upload new files. So for example, let's upload the GitHub logo. Okay, so now as you can see, the application it's still working, so we haven't lost our application. Okay, now what we are going to do is we're going to bring the EU cluster back. So we go to the EC2 console and we select all our instances and we turn them on. And now what we are going to do is we are going to go back to RHACM and we are going to see how the cluster goes from offline to online. All right, so our EU cluster is back to life. So let's see how the application looks like. So the uploader application, as you can see now, it's deployed again to the two clusters, EU and US. And if we go back to the application, now we can see um, how the uploaded files are still there. Okay, so files are here, so we can also upload new files. So for example, let's upload the OpenShift logo. So as you can see, we lost our primary site, but since we had backup site, in this case the US cluster, we were able to continue giving service during the downtime. And then when the EU site went up again, we were able to add it to the load balancing and having it giving service again without us needing to do anything. And now let's go back to the RHACM console. If we go to Observer Environments Overview, we can see that all our clusters are now running. We have 3 clusters and we have every pod is running. So everything, it's okay. And with that, the demo is finished. Thank you very much. Back to you, Ryan.
So, we've talked about a lot of cool tech, and Mario showed an amazing demo of how these all can be implemented together to allow for a multi-cluster capable application. One of the last things we want to look at is just all of these pieces together and how we got here. So starting back at RHACM, Red Hat Advanced Cluster Management will handle the management of our applications and the clusters. This served as our GitOps tool for the application placement. Strict load balancing rules are in place that will route our traffic based on specific health checks. If these health checks fail, then the load balancer will automatically route our application to the healthy cluster. The data replication of our uploader application that Mario showed is handled by Scribe. The replication occurs on a schedule and utilizes a secure communication tunnel and cross-cluster service name based off of the Submariner project in the global net. And here you will actually see links for the applications that we used during this demonstration. Load balancers were left out of this list because there are many options and potentially already one in place at your organization today. The first link is for the Scribe project. The second you will see is for Submariner IO. And lastly, the RHACM documentation. One key thing that I would like to touch on is that with future releases of RHACM, you may see a tighter integration of all of these components that we showed together. Thank you for watching this presentation.